Let's assume this situation. We have a long, straight, cylindrical wire. Again, what does it mean long? From the mathematical point of view, it means infinitely long. Basically, you just need to know, I don't know, the terminology. It's like, I remember in one of my classical mechanics courses, right, theoretical classical mechanics, there is a problem. Okay, the problem says there is a big bucket of water, and there was a bottle, right, oscillating, right? So you're supposed to understand that big bucket or large bucket of water, I don't remember exactly which word was used, right? But basically, from that word, big or large, you're supposed to extract that information, that basically your bucket is just an ocean, right? So when the bottle oscillates, the level of water doesn't change, or is not changing, right? So you just need to know, whenever a problem says long, it means infinitely long. If it's some large object, it's basically infinitely large, right? Large bucket, it just means basically ocean, right? Okay, so long, it means infinitely long. Straight, yeah, straight. All right, so then radius of the wire is given. Again, it's a cross section, right? And I try to draw a three-dimensional situation, right? And then current I flows, it's a total current, which is uniformly distributed over this wire. Again, every time we looked at the simplest possible situation with a uniform distribution of current. Because in this case, yeah, integration, the problem is significantly easier. Right? You don't have to do you don't have to integrate in order to find enclosed current. Right? And so we need to find the magnetic field, right? Because again, what does it mean we have current? Current, it's a motion of charges. Since whenever you have charges which move, of course, they create magnetic field around themselves, right? So, of course, there must be magnetic field. The whole space will be filled with magnetic field. And of course, there will be two parts of this problem. First, we need to find magnetic field, for example, outside, when R small is larger or equal than R capital, right? So we need to find magnetic field outside. And so now, how many approaches do we have? You remember now we have two equally strong, equally powerful approaches which can be used to solve this problem or any other problem if you want to find magnetic field. You can use Biot-Savart law, or you can use now Ampere's law. I told you in the previous lecture that once when I started teaching this course, I used Biot-Savart law to find magnetic field for this situation outside of the wire. It took me like 15-20 minutes of diligent integration, right? And students were looking at me with round eyes, kind of, what are you completely mad? So after that, I stopped doing this, right? Because using Ampere's law over here, usage of Ampere's law is much, much easier. Right. So again, it can be solved using Biot-Savart law. Yeah, but it's mathematically more challenging. It's easier to use Ampere's law. So we're going to use Ampere's law as a result. So first of all, it's a good habit just to write Ampere's law. B dot ds equals to mu naught times I enclosed, right? I can even frame because, yeah, it's a beginning. It's a fundamental law, right? And again, which step should we make first? We need to pick an Amperean loop. Without that step, we wouldn't be able to start integration, because integration over an Amperean loop. So if you haven't chosen the Amperean loop, then you wouldn't be able to start integration. And of course, I enclosed, the same story. Without Amperean loop, you cannot tell which current is enclosed, which current is not. Right? Okay, so we need to pick an Amperean loop. And I'm thinking which tools can be used to draw. I do it by hand. Okay. So first of all, an Amperean loop must be in the region where you want to find magnetic field. We want to find magnetic field outside, so Amperean loop must be there, outside. Then second, as I told you, you can use any Amperean loop. You will never be wrong from the mathematical point of view. From the point of view, is it legal to use Ampere's law? You can use Ampere's law for any closed loop. So strictly speaking, of course, you can pick any closed loop. But if you pick a complicated loop, then of course, most likely you will never be able to solve the problem. Right? You will end up with very complicated integral and no way of extracting magnetic field. So you need to pick the best possible Amperian loop so we can utilize, so that we can use the symmetry of the problem, cylindrical symmetry of the problem, right? And again, your gut feeling should tell you which is the best Amperian loop, right? It's a circle centered on the center of the wire, right? And with a radius larger than r capital. Okay, let me draw it. Not bad. Oh, slightly shifted to one side. But you understand, it's centered on the wire. And let's say of some arbitrary radius r small. So that's my Amperian loop. You know what? I'll probably also write it here. That's our Amperian loop. Amperian loop, right? Then what else do we have to make with this Amperian loop before we start taking care of that integral and the right hand side are enclosed? Previous discussion, we also, once you pick an Amperian loop, we have to make a decision about direction of the loop, right? Direction of integration. Should we choose direction counterclockwise or clockwise? Again, if you pick clockwise or clockwise, okay, neither of these directions is wrong, right? It just one would be slightly easier, one of the directions, right? You remember, once you pick a direction, that determines if your current is going to be positive or negative. You remember that right-hand rule? You need to curl your fingers in the direction of integration in order to determine which current is positive and which current is negative, right? Here we have only one current, which is uniformly distributed, but basically one current, right? Why would you pick a direction of integration so that your current was negative? It's not the best option, right? So of course it's better to pick such a direction of integration so that your current is positive, right? So if I, for example, let's say I pick clockwise direction. So if I curl my finger, right, that way, so my thumb gives me a positive direction for the current. So positive direction for the current will be opposite to what we have, to the direction of current we have. So it would make our current negative. I don't want to do that. Right. Again, at the end, you're going to end up with the same answer at the end. But I will say in a few words in a few seconds, right? But anyway, so don't use negative currents, right? So in this case, it's much easier to pick this direction, counterclockwise direction, right? So if you curl your fingers in that direction, your outstretched thumb gives you positive direction for the current. So in this case, our current is going to be positive, right? So let me show this direction. So this will be my direction of integration. Right. So immediately it gives us a direction of ds, right? Because direction of that ds is determined by your direction of integration. So I can draw over here, for example, this is my ds, right? So here is my ds. I can draw it here, for example. So ds. Right. Okay, yeah, we'll get back to the integration in a second. But what if, for example, if we picked opposite direction? If we picked a clockwise direction, Uh, you know what? No, I will say what I wanted to say maybe in a few minutes. Right now it's too early. It's too early. I need to first draw all the vectors, and then I will elaborate about this, about the second option. Right. Okay. Anyway, now we prepared preliminary steps, and now we're ready to actually start applying Ampere's law. Right. Usually, I start with evaluation of this integral. Right. So let me integral over the closed loop over the Amperean loop b dot ds, and now steps will be very, very similar to steps which we used to apply Gauss's law. Again, the first step will take care of what? It will help us to remove vectors, right? So after first step, we're going to have the product of just the magnitudes of these vectors. And then we will use symmetry. And during the second step, we're going to extract magnetic field from the sign of integration. You remember, we made exactly the same steps when we applied Gauss's law. Okay, so let's do it. And as we did in the Gauss's law, at this point I open my explanation box and I ask, let's draw, or should I say, let's draw all these vectors on the picture. ds is already on the picture. So now B, magnetic field, direction of the magnetic field. Okay, usually books, and this particular book, books say something like this. Because of the cylindrical symmetry, it's obvious that the magnetic field must be tangential to the chosen Amperean loop. Yeah, again, God's feeling should tell you that most likely it's correct. But usually at this point, I'm trying to justify that, like I did in the Gauss's law. And my justification, I'll probably write and draw here. Right, so let me digress for a few minutes to justify the direction of the magnetic field will be tangential. Over here, over there, over here, right? Tangential to the chosen Amperean loop. Okay, let me write. Okay, let me write. Justification that B is tangential. Tangential to our Amperean loop. Right. Okay, let me redraw quickly this picture. All right, basically the this wire. All right, so let's say this is my wire with the current, right? And let's say I want to find, you know what, let me estimate how much of space I might need. Why not? So let's say I want to find direction of the magnetic field at this point. Again, this is the wire, right? And this is the point where I want to find magnetic field. Direction of the magnetic field. Let me draw this auxiliary line which goes through the center of the wire, right? And now let me do this. Since we have uniform distribution of this current, so of course I can all the time I can pick, for example, over here, small piece of current. Very, very small piece of current. Why not? Of course I can take, and of course it will be just a infinitesimally small piece of wire, right, with current. So how can I find direction of the magnetic field at this point? Very simple. Again, for a second, forget about the rest of the wire with the current. So just basically very, very small piece of current over here. So how can we find direction of the magnetic field? You remember, it's very simple, right? So if you have a current like this, so you remember magnetic field lines form circles, right? And how can we find direction of these magnetic field lines? Outstretch your thumb in the direction of the current, and your curl fingers are going to give you directions of these magnetic field lines, right? So you'll get something like this, right? And if you're interested in the magnetic field, for example, at this point, just draw tangent line that will be magnetic direction of the magnetic field. Now, that's what I want to apply for this small piece of current, right? So let me draw one of these magnetic field lines. Right, so it will be, okay, I'll try to draw by hand. Right, so it will be somewhat, right, something like this. It's just basically one of these magnetic field lines. So I use dash line. So, and of course, magnetic field is going to be this way, so B, right? But then, at the same time, I can find symmetrically positioned similar piece of current over here, again, symmetrically relative to this line connecting the center and that's the point in question, right? Because again, we have uniform distribution of current. We can find similar pieces of current anywhere we want. So let me pick symmetrically position, right? And again, in order to find contribution to the net magnetic field at this point, I need to draw one of these magnetic field lines, but now for the green piece of wire, right? So it will be something like this, right? And this will be a green contribution, right? Again, since this distance and this distance are the same, currents are the same, right? So of course, magnitude of this B and that B are the same. So now let's add them up. Of course, radial components, blue radial component will be towards the center, green radial component will be away from the center. Of course, radial components cancel, and only tangential components are going to add each other, giving us the net magnetic field this way, right? So if you imagine here a circle, okay, Amperean loop centered on the center of the wire, this B is going to be tangent, right? So that's what usually I give as a justification of the fact that magnetic field is going to be tangential. But basically, yeah, it's a consequence of the symmetry. Okay, so now after this, I feel like, yeah, I can draw my magnetic field vectors. Okay, I can draw a few. So that's my B. That's our B, right? Okay, so now all the vectors are on the picture. Now I can continue, right? So I can write, since B, we can see, is parallel to ds, right? So the angle between them is 0 degrees. I can write, so B dot ds equals to B ds times cosine of 0 degrees. B times ds times cosine of 0 degrees. All right. Okay, I should draw these vectors over here. Okay, now let me close explanation box. And actually, no, cosine of 0 degrees is 1. So as a result, we have just a product of magnitudes B and ds. Okay, so now I can continue. So integral over the closed loop, B ds. At some point soon, I need to change marker. It's getting a little bit not as dark. So now, next. You know what? Now probably it's time to digress a little bit and tell you what would happen if we picked opposite direction of integration. Opposite direction of integration. Now I think it's time. Look, if we picked this direction of integration, clockwise, first of all, our current would be negative. So we will have minus on the right-hand side of this law. But also at the same time, what will be direction of ds? Since we choose the direction of change the direction of integration, of course, ds will be that way. But B will be still that way. Because our direction of the magnetic field cannot be changed by our imaginary Amperean loop, right? And our imaginary this direction of integration. No, nature doesn't care about our imagination, right? Just God created nature this way and it runs according to these laws, right? So magnetic field will be still that way, but ds would be in the opposite direction, right? So of course, in that case, if you draw properly, b that way, ds that way, so they are opposite. Of course, over here I would have to draw b is anti-parallel to ds. And of course, over here I would have cosine of pi 180 degrees. Cosine of pi is -1. And you will end up here with minus, right? You'll have minus in front. So now you will have a negative value of the integral. You have minus over here. And of course, minus here, current is negative. So minus this minus and that minus, of course, they cancel each other, giving us plus. As a result, even in that situation, you will end up with exactly the same answer, right? But if you pick that direction, I guarantee that probably 90% of students, they wouldn't notice that minus it will also pop up over here on this side. They, of course, most of the students will end up with that minus at the end, and they will try to hide it somehow, right? Maybe just erase it at some point, right? So don't do that, because in that case, yeah, as I said, chances that you're going to lose minus over here are very large. So it's better to make current positive, B and ds parallel, and solve this problem without those extra minuses, right? But again, in both cases, you will end up with exactly the same answer. So now back to this. Now let's use the symmetry one more time. And okay, imagine yourself, for example, sitting over here at this point, right, on the Amperian loop. And look, of course, this magnetic field is created by this distribution of current, this uniform distribution of current, right? Right. And now move yourself, imagine, let's say you move yourself to this point. And again, look at the distribution of current, which creates your magnetic field at this point. Will the distribution of current be any different? It will be exactly the same, because we have cylindrical symmetry. So if you have exactly the same distribution of current like here, of course, the magnetic field strength over here and here will be exactly the same. Or any other point. But again, its strength, magnetic field strength will be the same, because vectors, magnetic field vectors are not going to be the same. They have different directions. Here magnetic field that way, here magnetic field this way, here magnetic field that way. But since we already managed to get rid of vectors, now we have only magnitudes. So now we need to take care only, or look only at the magnitudes of the magnetic field. And magnitudes will be exactly the same. It doesn't matter where you are on the Amperian loop, this point, that point, at any point on the Amperian loop, magnetic field strength is going to be exactly the same. So we can say that B is constant in this integral, because in this integral we are on the Amperian loop. We're not allowed to step away from the Amperian loop, right? In this law, we all the time stay on the loop, right? But again, don't write that magnetic field is uniform, because sometimes I see students write, so magnetic field is uniform. No. Magnetic field is not uniform. If you step away, for example, over here to this point or this point, of course, here magnetic field gets stronger, here magnetic field gets weaker. Uniform magnetic field, it means the same at all points. Right? No, magnetic field is not uniform. Just magnetic field is constant. B equals to constant. And I will add on the Amperian loop. Only on the Amperian loop. Right? So now we all are set for an extraction. So we prepared ourselves to extract magnetic field, right? So as a result, since B is constant, so we can extract it from the sign of integration. So we can extract it from the sign of integration. Okay, let me finish this. So that's the important step where we do our extraction. So B, integral of the closed loop. Maybe I will write underneath Amperian loop, of course, right? And now, what's the value of this integral? Again, it's still calculus 3. Actually, still here there are plenty of work that needs to be done in order to calculate this integral properly, right? But we use our high school knowledge because we know the meaning of this integral. It's just adding small ds's. When you move around the loop, where is my loop? No, it's in front of me, right? So what's the meaning of integral? So in this integral, you're just adding ds's, right? Small ds, I know, micrometers, plus small ds, plus small ds, plus ds, it's small length, right? Small section, plus, and you keep adding these small ds's around the Amperean loop, around the circle. Once you finish adding all these ds's, what are you going to end up with? The circumference of the of the Amperean loop. Circumference of the Amperean loop. So it must be 2 pi, okay, 2 pi, and be careful which r, because sometimes students just pick whatever r closest, right, and use that. Now in this case, we are on the Amperean loop, radius r small. So be careful at this point, right? 2 pi r. So that's the value of this integral, b times 2 pi r. So we finished evaluating this integral, and now, according to Ampere's law, it must be equal to mu naught times I enclosed. Mu naught times I enclosed. So now that's what we have, and after the break, we will see what is I enclosed. And you know what? Before I start calculating enclosed current, let me discuss this. I told you that you can use pretty much an Amperean loop of any shape, right? And I told you that if you use any other shape other than the circular shape, most likely you will never be able to get the answer, right? You will get somewhere, get stuck in math, right? You will never be able to get out of that, right? Look, even for example, let's say you instead of a circle, you pick an ellipse. What would be in this case in terms of our steps? B, magnetic field, is still going to be tangent to this circle, because with our choice of an Amperean loop, we cannot change the nature. We cannot change direction of the magnetic field. Magnetic fields are, I know, determined by God, right? So somehow he created all this nature, right? So in this case, magnetic field all the time tangent to the circle, right? But if you pick ellipse, right, as your Amperean loop, then ds is not going to be parallel to B. It will be parallel probably in 4 points. And this point, and that, for example, only 4 points. In the rest of the points, they're not going to be parallel. So it means that the first step would be impossible. So I wouldn't be able to write something like this. And then the second step, I would never be able to tell this, that B is constant on the Amperean loop, because over here, let's say ellipse goes up here, right? So of course, this point is farther from the wire than, for example, this point, which is closer to the wire. Of course, magnetic field strength is not going to be the same. So this point, this step where we extracted magnetic field would be also impossible, right? Would be illegal, right? So as a result, both of the steps would be impossible, would be incorrect, right? And of course, as a result, it means that mathematically would be ridiculous, significantly more challenging, right? So it means that, we need to be smart and pick the best possible loop. In this case, circle is the best possible. Right? Okay, so now back to I enclosed. So now we need to find I enclosed. Again, usually at this point I ask, so guys, find enclosed current. And some students, like with the Gauss's law, at this point, they just take this equation, okay, this expression, and solve I enclosed in terms of B. They just move mu naught to that side. But again, it's not wrong, it's just useless. Because you write sort of preliminary unknown in terms of your global unknown. Global, it means that we need to find it at the very end, expression for the magnetic field. It's not wrong, but it's completely useless, right? So it's basically, if there are some points assigned for that step of finding enclosed current, it just basically means 0, right? So don't do that, right? So now we need to find I enclosed, basically using the definition of I enclosed. It's that amount of current which is physically within the Amperian loop, right? And in this case, it's trivial. What's the total amount of current within the Amperian loop? Amperian loop embraces the whole current. The whole wire is, where's my, so here's our wire, right? And our Amperian, okay, I can use actually this. And our Amperian loop is this. So the whole wire is within. So it means the total current I, this whole current I is an enclosed current. In this case, it's very simple. Right? See that? In this case, the total current I is our enclosed current. So I in equals to I. And where that current is, it doesn't matter in the Ampere's law, right? So if some current is over here, some current is over there or there, it doesn't matter. As long as the current within the Amperian loop, just count it in towards the enclosed current. But of course, in our case, we know that the total current is the total current I is within the Amperian loop. So we just use the total current. Okay, so now we just plug it over there, and as a result, we will have, so of course, B times 2 pi r equals to mu naught times I. And of course, in your answer, this subscript enclosed must not be there. Your answer must be written in terms of what is given. So if you substituted I instead of I enclosed, this I must be at the very end, because I see students very often they still use I enclosed at the end in their answer. No. The answer must have only what is given in the problem, and the variable, in this case r small, basically a variable. Right. Okay, so now we can solve it for B. B I can write as a function of r equals to mu naught times I divided by 2 pi r. Right. Okay, so now that's the final expression, and that's what we've been using already, right? In our problems on Friday, right? But again, this can be derived using Biot-Savart law, but that derivation is significantly more complicated. This, without my justification explanations, it should take like, I don't know, a few minutes. But of course, I need to emphasize that this is for r larger or equal than r capital. Right. Okay, so now part B. But if you have questions or something is not clear, tell me. So now B, we need to find magnetic field outside, which we wrote it. Okay, for r less or equal than r capital. So basically, no, now it's inside. Sorry, I said outside. Now we need to find magnetic field inside. So again, Ampere's law, and the first step that we have to make, we have to pick an Amperian loop. And of course, it must be in the region where you want to find magnetic field, right? You know what? Let me use now blue as to show the Amperian loop. I don't want to draw a new picture, so I will recycle the same picture. Now recycling is popular, so I will also recycle pictures. So that's now my Amperian loop, right? And of some arbitrary radius r small, but of course r small now is smaller than r capital, right? So let me show it somehow, r small. Right? Then second step, direction of integration. And again, the same arguments. I don't want to have negative current at the end, right? But again, in that case, minus will pop up in front of this integration. Minus and minus give us plus, but again, chances that you're going to make a mistake in that case significantly larger. So let's reduce those chances. all right, by picking the best direction. In this case, again, best direction is counterclockwise. So this will be my, and as a result, this will be my ds. Right. Okay, magnetic field will be still the same tangential. Right? Again, since we picked this circle centered on the wire, of course, magnetic field will be the same. So B, B, B. Right. And I claim that all these steps from this point all the way to this point, all these steps are going to be exactly the same. You can just rewrite them right up to this point and write this. Of course, I'm not going to do it. Right? I will just write this part and I will write in exactly the same way. So I will write integral of b dot ds over the Amperean loop, and I will write the same steps, exactly the same steps, right, will lead us to b times 2 pi r equals to mu naught times I enclosed. Right, so immediately to this point. Exactly, not a single symbol is going to be different. So now, as a result, we need to find I enclosed. And now that's where troubles are. Lots of troubles usually. All right, so here the total current was enclosed because, yeah, the Amperean loop was outside and the whole current is embraced. But now, where this I enclosed, let's just look at the picture. It's this current. Let me maybe highlight it with blue. Now it will be too much of blue. I'll try to use light lines. So that's where Q enclosed. Wait, I'm still using terminology of Gauss's law. I enclosed. Sorry. That's where I enclosed, right? Within that blue Amperean loop. And of course, this amount of current is smaller than the total current, because the total current is distributed over the cross section with radius r. This now I enclosed is distributed within the cross sectional area with radius r small. See that, right? Okay, so we need to find that amount of current only. And now, again, as I said, that's where most of the troubles are, most of the mistakes. Now, of course, during the virtual classes, it's easier because students have everything, right? So notes and so on. But whenever we have classes at school, lots of troubles at this point. So, but again, it's very simple because it's all about this formula. You know what? Let me write it here somewhere. Definition of current density. It's a current divided by the area over which. So current density, you take current and divide that by the cross-sectional area over which that current is distributed. That's it. So we just need to use this all the time. Or if you want to find current, so how can you find current? You take current density and multiply it by the cross-sectional area over which that current is distributed. So everything that we need to know in order to find I enclosed is in this formula, nothing else. And then the rest is just a logic, simple logic. Right? So let me give you sort of two ways, although it's basically potato, right? But still, some students find first approach is easier, some students find the second approach is easier. All right, so I'm going to do this. So I enclosed. How can we find it? I enclosed, you take current density and multiply it by the cross-sectional area over which I enclosed is distributed. Current density is exactly the same. So for now, of course, we don't know current density, but in a second we will be able to find that current density. But again, you see, I enclosed, it's a current density times cross-sectional area over which enclosed current is distributed. So times area with radius r small. It's a cross-sectional area over which enclosed current is distributed. Area with radius r small. All right. Okay, so now how can we find current density? Current density can be found using a current which is given in the problem. We know this current I is distributed over the whole wire with radius r capital. Again, the same formula. So now, but now we need to find current density and using the total current. So total current divided by the cross-sectional area over which the total current is distributed. It's a circle, okay, area of the circle with radius r capital. Again, it's all in this formula. You just apply it either for total current or for enclosed current. Nothing else but this formula applied in a different form for different currents. So it's a I divided by the cross-sectional area with radius r small. Right? Okay, so now let me plug it. All right, and as a result, I will have I and ratio of these areas. All right. Area of the circle. Again, guys, be careful because quite a few students every semester making the silly mistakes using, I don't know, circumference of a circle or area of the sphere or something else, right? Just the wrong formulas, which yeah, which is not very good. So I times pi r small squared times pi divided by pi r capital. So as a result, okay, I need to invade this part of the board, which is not good, but not too bad. So that's the amount of current, enclosed current. Some students find the second approach easier. Like I remember some students came to my office asking, so how can they find this I enclosed? When I presented the second method, which is basically like the first one, they found it's much easier. They found that method is much easier. So we can find current density. Okay, here's the formula. Using first the total current, like here, or we can use the enclosed current because current density is exactly the same. We have uniform distribution of current. So we can find current density using two different currents, and then since current densities are the same, we can equate them. Right? So first we can find using the total current, I divided by area with radius r capital. It's one way. But at the same time, since current density is the same, it's uniform distribution, we can find the same current density using I enclosed divided by a cross-sectional area with radius r small. And again, since these current densities are the same, so of course I can put equal sign between them, and these two sides of this expression can give us exactly the same here, right? So you just need to solve for I in. So a sub r goes over here, and we will end up with exactly the same formula. So I in equals to I and the ratio of these cross-sectional areas. So it will be eventually exactly the same like what we got over here. So some students find this easier to understand. Okay, so it's up to you. But if on the exam you just write, so the enclosed current equals to that, without showing any explanations, yeah, I wouldn't be very happy because you didn't explain. You need to explain, right? So what you do. Right? Of course, it doesn't mean that you need to write an essay, write what you've done. No, no, no. From the mathematical point of view, right? I know enough physics and mathematics in order to understand what you do if everything is diligently presented. There is no need to write an essay. So now that's what we need to use over here. So now let me rewrite this. And justification is no longer needed. I can erase this. So now I can continue this. B times 2 pi r equals to mu naught. And now instead of I enclosed, I write I, and the ratio of these squares. I just rewrote this. Right. Okay, 1r is cancelled. Right, so r here. And that's it. Yeah, nothing else can be cancelled. So from here I can write b as a function of r will be equal to constant mu naught I divided by 2 pi r squared. What else? That's it. That's it. And now times r small. Yeah. So I can frame it. And of course, I need to add that that is correct only when r is smaller or equal than r capital. So these are basically given constant, given, and so it's a function of r small. So within the wire, magnetic field grows linearly, but outside of the wire, magnetic field decays as 1 over r. Let me plot magnetic field versus r. So now let's summarize this. So this is B, this is R, and let's say this is R capital. Actually, I can draw this dash line. And so inside this magnetic field increases linearly. So it's a proportional to R, and then it starts decaying as 1 over R. So it's proportional to 1 over R. So that's how magnetic field changes. Inside and outside of the wire changes with R. R small.
Professor, you're muted.
I muted myself. Yeah, it's basically that's how B changes with the distance from the wire. Yeah, R. It's a distance from the wire, from the center of the wire. Yeah, very important, from the center of the wire. You know what? Yeah. Let me look quickly at another case of finding I enclosed. Although we looked a couple of classes ago at the end of the class, but let me remind you that that's where it's can be used. Where are my markers? Okay. Let me put a new bullet quickly, right? And what if we have this situation? What if you have a wire of this cross section? Okay, good enough. All right, so let's say this radius what? B, and this radius A. All right, and so this is the wire, and the metal is here. So it means that current flows, of course, you know, current flows only through the metal, right? And let's say current is this way. Again, the total current is given. This is a hole. Of course, current cannot flow through the hole, through the vacuum, right? So, and let's say we want to find a magnetic field, for example, inside of the wire of some arbitrary radius r again. So that's our Amperean loop, right? Again, direction of the integration, I will pick counterclockwise, so that's Amperean loop. And so all these steps, again, because symmetry is the same, right? So all these steps from here all the way to this point, for that case will be exactly the same, right? Exactly the same. So again, I will write, so let's say we need to find B for this situation. R is larger than or equal than B and smaller and equal than A. So let's say for that range inside of the wire. Okay, so now again I will write similar, and I can actually probably should draw magnetic field, right? So this will be my again magnetic field B, because the symmetry is the same, so it will be still tangential. So in a similar way, you will get to this point, right? So again, to this point, B times 2 pi r, B times 2 pi r equals to mu naught times I enclosed. And now, of course, again, what's the value of I enclosed? And if you look at your notes, I think at the end of Thursday, a couple of classes ago, I think, at the end, we looked at this situation, right? So let's find I enclosed. Again, the total current is distributed between this circle with radius B and circle with radius A. Again, uniform distribution. But we need to find only current, enclosed current. So it means it's a current between a circle with radius B and a circle with radius R small. Okay, let me highlight this region sort of like this. So that's where our I enclosed is, right? So how can we find that? Again, basically it's all about this formula. But now we need to look carefully and every time extract this hole, because inside of that hole there is no current, right? So let me use, for example, this first. So I can write, so I enclosed equals, again, current density for now is not given, but I will find it in a second. So what do we have to do with current density in order to find I enclosed? In order to find current, we need to take current density and multiply it by the cross-sectional area through which this current flow, or over which that current is uniformly distributed. So it's the I enclosed, so we need to multiply it by the what? The area, this highlighted area, bluish. Right? So how can we find that area? Again, it's your that problem. It's a area of the circle with radius r small, and subtract area of the circle with radius b small. So it's a, you see, we need to extract the whole area with this radius, area of the circle with radius b, a sub r minus a sub b, right? So that's the area through which or over which that current I enclosed is distributed uniformly, right? So now current density. Current density, I'm going to find like here using the total current, because I know that the total current I is distributed over which cross-sectional area? It's this between circle with radius A and circle with radius B. And again, there is no current in this inside of the circle with radius B, so we need to subtract it, right? So I need to take the total current and divide that by the area of the circle with radius A. minus area of the circle with radius b. Right. Again, we've done it 2 classes ago. I just want to remind you that. And that point, I warned you, we're going to use that in a few classes. And that's the point when we need that. Right. So you see, here I remove the whole minus a sub b, and here I remove the whole area of the whole. Right. And of course, we know this area is pi r squared, right? Okay, it depends on which r you have. Okay, so now let me, of course, we can plug it. We'll have, so what, I divided by, wait, that's too big, divided by a sub a minus a sub b. So current density times a sub r minus a sub b. Okay, so now let's write explicitly all those pi r squared. So it will be I divided by, okay, I will factor out pi immediately. A squared minus b squared, and here pi r squared minus b squared. So pi goes, pi gets cancelled. Okay, I need to erase this. So as a result, I enclosed has this more complicated structure. R squared minus b squared divided by a squared minus b squared. So that's in I enclosed, so now we can plug it here and solve it for b. I'm not going to do it, right? And look, this case, this case, it's a special situation of this situation. Basically, how can we get from this case, that case? B must go to 0. If b equals to 0, whole disappears, right? So we have this situation. And look at the I enclosed. If b goes to 0, this b 0, that b 0, so I enclosed will be equals to current times r squared divided by the radius of the wire. In this case, a squared, but in this case, it's I erased it. Okay, here, let's use that. But in this situation, instead of a, we have r capital. But again, what's the difference, right? So if b equals 0, this situation turns into that, and this formula gives us this case, right? This I enclosed. Okay, you see, it's all about this definition of current density. Sometimes you need to find current density, sometimes you need to find current.